Hi everyone. We're Philipp and Frieda from Mimimi Productions, and we're going to talk a bit about shadow tactics in this next hour or so. Many of you probably saw a bit of shadow tactics yesterday already, but we're not actually doing a mobile port, just to make sure everyone knows that. We're actually working on our next big project, which is similar genre of shadow tactics. And we just wanted, before diving in, share our experiences and what we learned from shadow tactics, and just talk a bit about it, what we will take into the new project and what we will do differently and stuff like that. So we'll go over some of the more important systems we implemented and some nice-to-have features. And yeah, let's dive right in. We have some interesting facts that you might come across when working on a kind of large-scale project. For example, when you extend your editor, you build maybe some tools, and, well, sometimes it might be too much, so take care. Or maybe if you have kind of complex logics in your system, you generate some code, and then you end up with script files with over 50,000 lines of code. Yeah.
So first, we want to make sure you all know shadow tactics. Yeah, it's a real-time tactics game where you control multiple characters, and they have different skill sets, and you kind of sneak your way through the Edo period in Japan. It's stealthy, it's a hardcore PC game, so we wanted to have really nice graphics, and we ported it later to the consoles, but for us it was always PC first. So we had some things coming up to do the port, because it wasn't that easy just clicking, yeah, we choose build for Xbox and that's it. It's not that easy, actually. Yeah, we launched last year on this December the 6th, and we have the console release coming up. Hopefully, it all goes well in the certification, because we're currently in the certification for PlayStation in US, and it gets quite the time's kind of up. They have to hurry.
I'm sorry, we just got. No, that's okay.
So, Mimimi Productions obviously didn't start with shadow tactics. It was a really large project for us, and we started with mobile in 2011. And we did the Da Vinci, which won the Apple Design Award. And this was a foundation. This was a ground to do the next step on. And then we developed several mobile games, but we felt we wanted to develop PC games. So we went to core games, and the first PC game we did was The Last Tinker in 2014, and now Shadow Tactics. Yeah, in all this time, we always developed with Unity, so we have like 6 years of experience in the company, but Frieda and I'm not that long there. Yeah, Mimimi Productions is currently a team of 20 guys and girls. And at the time of Shadow Tactics, we had 3 game designers, 4 artists, and 4.5 coders, because we had some interns. And we divided this in certain areas of skill set. So Frieda, for example, did all the AI stuff and the build pipeline. And for the next project, he is also the technical director. And I'm one of the gameplay programmers, so all the player abilities and what random stuff game design comes up with.
Okay, so let's quickly give you an outline of what we're kind of talking about. First, I will show you our asset import pipeline, what our workflows are, what benefits we got out of them. Then Phil will talk about our editor tools, the most used stuff and most useful stuff for game design and level design. Then I'll talk quickly about our build pipeline, because it's quite a complex system, and when you have like 13 target platforms, you kind of need to automate stuff. And this goes from like updating S4N repositories to uploading the finished builds to Steam. Then Phil again will talk about some code structure, how we maintain complex logics in our project, and how we use behavior trees for the character logics. And lastly, I will talk about optimization and the console part. There was a lot to do, and yeah, we'll go into that a bit. So, okay, so first off, the asset pipeline is one of the most important things in a game, we think, because the assets are usually what is the foundation of everything you do in the editor. Because you just, when you get an asset in the editor, level design or game design will want to use it immediately without worrying about settings or where it is defined or something like that. So if you don't use like something like a strong naming conventions and automated import settings, you end up losing assets because nobody can find them or because nobody can use them, and it's generally very hard to maintain if there's not some very basic structure. We learned this the hard way with in the last Tinker, where we didn't automate everything and had to change some settings on specific assets later on, and this was very hard to do and very error-prone, missing some assets, and so it was clear going in with also the asset overview. So this is our basic number of assets per type, which shot up pretty dramatically for Shadow Tactics, especially in the textures and audio department. For audio especially, because we used full voiceovers for English and Japan, which amounted to over 5,000 files each. So it was pretty clear we couldn't handle anything manually with those amount of assets. I'll just go into the basics of asset importing. This is at the base of all our different asset pipelines. The asset post processor gives an API for getting events before an asset is imported and after an asset is imported, so you can do stuff in these parts. The user data is stored in the .meta file besides the asset, and there you can write useful information for later usage, like which preset is used to import the stuff or something like that. And everything we do is based on naming conventions, so we always use some specific prefixes for textures or audio files, and based on these prefixes we apply our import settings. So I'll go into a bit more detail for our texture imports and audio imports now. The texture imports is based on various presets that apply specific settings that have been talked about with art and code to ensure it's very good quality and whatever we need. First import is based on the prefix, as I said, but after it's been imported once, we can change the preset and it's saved on in the user data again. Artists only use the presets, they never change any specific import settings. If they want to, it's getting overridden by the presets. If they actually need to change specific settings, they can use the custom preset and then change the import settings how they want. And the audio clip import itself is pretty basic. We just looked up in the Unity manual what they suggest, what you should do for various sound effects, music, voices, whatever, quality settings and stuff like that, based on clip properties, like length and stuff. It's very useful information. So this is what we do for every audio clip. But audio has like a lot of uses for sound designers and game designers. They want to use many different settings on them, play them in a level differently and stuff like that. So we needed to add more functionality to our audio clips. So we implemented a audio clip container, a custom one, which gets created every time an audio clip is imported. If there's not one container that has the same name as it already, if that's the case, we can use clip variations. So if the clip has the same name with a different number at the end, then it's added to the same container. And when you want to play the container, it just selects one of those random. So you can have 5 different explosion sounds and trigger one explosion, and it's always random from these things. And it also lets us add any setting we want to these things. There's a lot of stuff in there, like volumes, pitches, randomization of everything, animation triggers, like an animation plays on a character and it's automatically playing the sound as well, and fading, emitter following, and stuff like that. And it's extendable to whatever you want. Also, a big benefit of this setup was that we could change the voiceover files, clips, pretty easily, even during runtime, for when you want to switch the spoken language in the game from English to Japanese or back. We just take the 4 clips and put the Japanese ones in. It's pretty easy. To show you a bit more how we use strong naming conventions and prefixes, this is a bit more in depth for the audio files. The first prefix, SFX, is for telling the importer this is a sound effect, so it can apply a bit more compression or other stuff. The second prefix, the generic, is used to select the audio mixer that is later used to mix the audio together during runtime. And the third prefix is used to select the audio source prefab through which the sound is played during runtime. There are like 19 different audio sources currently, which have various different settings, ranging from 2D audio source, 3D audio source, different ranges, priorities, stuff like that. And it's all automated. Sound designer can just drop a new file in, and it's kind of done, and game design can use it instantly. So as a conclusion, again, naming conventions are really important, even if you maybe don't want to use a custom import pipeline now because your project isn't that big already yet, I guess. But maybe you want to do it later, so just use naming conventions. It's really, really useful. Structure your asset folder so you can use your assets, automate stuff. Everything you automate is less error prone because you implement it once so that it works well, and if you do it manually, you always leave one bool out or use a slider wrong or whatever. You do many errors. And when using presets, it's pretty easy to change stuff later on if you decide this audio clip, like the sound effects don't need that much compression, or music files need to be louder or something like that. It's pretty flexible that way.
So as soon as the assets are inside of Unity, you can start working with them. And a scene in Shadow Tactics has about 9 to 39K transforms, with an average of 30 and 100 NPC behaviors with a maximum of 161 and about 50 custom script logic. So there are a few things to ensure that you not wake up in a mess of thousands of game objects. They're named with weird names you long have forgotten the meaning of. So the first thing we would slightly touch is our use of the hierarchy. This is kind of obvious, because the hierarchy is a nice thing to just structure things, and we used naming conventions to generate all the structure in every scene like the same way. So the game designers always know, okay, there is the gameplay object, under this the level areas, under this there's save versus no save, so we can save the whole game. and we don't have to decide on runtime which objects we have to save, because they're dynamic and other ones are static. And yeah, it goes up all the way, and pretty on a depth about 8 levels of parents. And yeah, in the end, this worked pretty well. So why are we talking about this? Hierarchy is pretty obvious, but when porting to the consoles, we had a really big problem there, because when you move an object with about 6 parents, it is really slow, because Unity has to apply all the transformations of all of the parent objects in the moment you move the object. And with hundreds of NPCs and skills under it, this adds up pretty badly. So we worked around this by reparenting all the stuff that doesn't need the structure at start during runtime, and reparent it out to the save root, so it still can be saved, but yeah, we flattened all the things. And another thing we had a problem with was that every transform that's in the scene has an overhead for us to save and load, because there's data we just don't need. They're objects only for structuring. They don't need to have a position, rotation, or scaling. And yeah, so our save files is filled up with thousands of transform with default positions, and we are currently thinking about how we could fix this. So we're thinking about to use less transforms again, but this would just destroy our structure we had. And so what we're currently thinking about is creating something like fake folders. So there are transforms that are not really transforms. So in the left view, we have these folder things, and they're just for structuring the scene. But how exactly this would be implemented is just open. But most likely, it will end up in some tool to handle the new hierarchy. And we already have many tools there, but in the process of creating this talk, we just went through all of them, and we're like, this isn't used anymore, this is from Last Tinker. And so we structured them in categories. And what we want to show with this is there are some categories you might not think about when starting a larger project. And you most likely will end up with tools in kind of every area one can even think about. It's getting from just the game designers having tools for placing certain things like routine systems easier, to the import pipeline we already heard about, or project-dependent things like, okay, we have this jumps in this current project. We won't need this tool again in the next project, but it's just nice to work with it. Yeah, and stuff like fixing, because when code refactors things to just improve the complete structure of the project, you might end up destroying some scenes, and you don't want to fix anything in the scene by hand, so you run through all of them and fix this automatically. So one tool we want to focus is our node editor. We started on Last Tinker with a command system because it was easy to implement, and we thought, yeah, this could get really useful, and we just took it over to the next project. And the command system had a few problems because they're just components on game objects, so we don't see what triggers my command. Because I only see, okay, I'm in this game object, even if I add logs, and I'm inside this command that logs. But I don't know where this command was triggered from. And so I just end up like, okay, I'm there, but I don't have any overview of the whole commands of the project. And we really needed that. And it was hard in Last Tinker, and with shadow tactics being more complex, and we thought, okay, shadow tactics might have more complex logics, we would have to create something to overlook all these logic things. So we ended up with our node editor. Why write something like this ourselves, were you thinking? Because there are many things on the asset store that do just that, and but at the same time, we already had all these commands in our trigger system, and we wanted to use them in the next project because we all know them, we know how to use them, and so all these tools in the asset store often don't go well with your current project, your current code base. In the end, we had a nice editor that just shows the inspector inside this other editor view, and for every class that every class that implements certain things, like, okay, that are commands, they get these pointers to each other. So this can get quite big, and the editor is kind of really shitty. That's probably a drawback of creating it oneself, because actually you want to focus on your project, and then you create this thing, and it works. But when doing large logics, it just hangs, and it's a low performance thing, and still it is very flexible, and we will later see another thing we did with the same editor, which wouldn't be possible with another node editor that we just bought. So the conclusion for this is, use custom tools for what you do the most. And with custom, I mean, you know your project, you know what's really helpful. Sure, the asset store is nice, it's awesome. But sometimes you also, it's more like an inspiration place, you know? You click through it and you think, wow, this would be nice, and you implement it to your code base, because otherwise it would be just something to clip it on, and it would be rather weird to have there. And don't underestimate tiny helper tools like the one at the bottom. We don't know how to use Unity without it. Every time I'm working on a small project, I'm like, these buttons, they're not there. And I can't reset my position and rotation, and it's so much easier with that. Yeah, build your own tool base.
Okay, while we're on the topic of tools anyways, I'll talk quickly about the build pipeline. First off, why build a build pipeline? This one, for us, evolved pretty naturally. So first, we just needed to apply some settings for each scene before building, which was actually, while working in the editor, this was done automatically every time you pressed the play button, but we couldn't do it automatically for the build process yet. So we added a automate script that just iterated every scene and applied some settings, and then started the build process. So this was the first step where it started. Then, after adding more scenes and getting the scenes getting bigger and stuff, we encountered some pretty long build times already in the first half or 1 year of development, which approached like 2 hours at a time. So we kind of needed to run the builds on a different PC, so it wouldn't just block a developer for 2 hours when he needed a build. So we implemented a remote script. You can tell on your PC the build server that it should just build the thing, and that was done for a while, and we were pretty happy with that. Then there come other requirements, like building for multiple platforms at once and not having to issue a build every time when you need like Windows, Linux, and Mac at the same time because you want to publish them. And stuff like uploading to Steam after the build is finished. So this got pretty complex pretty quickly. At first we started with some batch scripts, which is pretty simple to set up and use at first, but as soon as you encounter like some for loops where you iterate over platforms, for example, it's getting pretty complicated. So we moved to C# applications to just have a more sophisticated tool to work with. We actually also never really thought about using third-party tools like Jenkins or something like that, because it just was such a gradual requirement changes that it was never like, oh my god, this build pipeline is exploding, we need to buy another tool or use another tool or whatever. So this is at the moment our build launcher. It's based in Windows Forms and C#. Yeah, this was really useful for easy UI iteration, adding new features in, just putting another checkbox there, putting another button there, another select box there. It supports many various stuff like selecting multiple platforms and then version numbers and stuff like that. And you just click launch build, launch remote build, and it sends a remote task scheduling to the build server, another PC in our office. And there we run a C# console application that just iterates over these steps we give it. This is kind of probably pretty generic. We could use it for other projects as well, but there are some steps we needed to include here, but more on that later. So at first, this just like updates the repository if you need to, or revert stuff. Then it generates some code. The code trees, Phil will talk about that a bit later. And then it starts Unity and runs a Utomate plan. More on that also later, like soon, in the next slide. After Unity is done building and stuff, we zip the builds, store them on our network drives to have them secure and ready. And then we start uploads to Steam for every build, and it's uploaded separately. And then we can, I don't know, tell our QA to, here's a new build, check that out. So what's happening in Unity itself is managed in Utomate. Utomate is another tool we already used in the last Tinker. This is very flexible and very, very useful for automating stuff in the editor. It has plenty of pre-built actions and stuff you can do with it, but you can also very, very easily extend and write new actions for it. So what's actually happening here is we generate some more code, first of all. This is for safe loading, to make it run even faster. Then we update some prefabs, like audio reference stuff, and I don't know, just update some stuff that it's actually correct when you build. And then we iterate over all scenes. This is the stuff we had from the very beginning. In every scene, we do stuff like baking nav mesh, doing some scene cleanup, removing objects that are only needed in the editor, doing some setup for safe loading, applying lighting data, and all this pretty stuff. After that is done, we start iterating over the different platforms, like when we want to build for Windows, Linux, and Mac. This runs 3 times for those platforms. And this just does some asset shuffling for various platforms, sets up some build settings, and then builds actually the player with the Unity build processor. And after that is done, we do some platform-specific post-processing, like copying libraries to the correct folders and stuff like that. And yeah, that's pretty much that. Again, it's very important, or it was very important for us to automate all this stuff because it's quite complex, as you probably can tell now. And it would just not be feasible to do anything of that manually every time you want to build. So, yeah.
So obviously, all of this is built on code. But our code at the start of Shell Tactics or the end of Last Tinker does look quite different to the code we write now for behaviors or player logics, and yeah, we want to look into that. So in the past, we did Last Tinker. We were a small team, and 3 coders did all the work. one for the player and camera, one for AI, and one for additional gameplay. And the player logics was built by the approach of divide and conquer, so we had many different components that all did their thing, and they were used and managed by one big player manager, which was kind of like a state machine, but still, this were 5K lines of code, and it wasn't maintainable. So we thought for the next project, we do have to change things, because we never really had an overview of the player states and which state we are currently in and what will come next. And so the debugging and bugs fixing was rather tedious and complicated, and yeah, we need to enforce a better structure. That was the thought. So then came shadow tactics, and the ground we built up on was we had a different coder team with the coders from before were like now the managers and kind of the directors, and had to do other stuff. And we had more coders, and the project was complex, and the characters did have various skills that they shared with the NPCs and all this stuff coming together. The risk was too high. We needed something to really always know what is happening. So what we thought we would need to do more complex characters was something that is fast to implement, that is actually enforcing a structure, so no coder can say, oh, well, I can hack this into rather fast, but in the end it's just broken. We need something to be able to maintain modularity, so we can use certain things for more than one character. Yeah, it should run pretty well, especially if porting to the consoles. And we wanted to have a visual representation. And this one got us to think about, okay, we have this node editor from before, and as we wrote it ourselves and as we built it upon objects, and it was easy to just visualize other things with it. It was really generic. So we used it to actually visualize our Me trees. They're just default behavior trees, nothing really special. So if you're new to behavior trees, you can look that up in Wikipedia, or a very nice Gamasutra article from Chris Simpson. And we had some specialties inside there, like our nodes are actually only delegates, so we can call everything, kind of, that has a certain structure, so returns a certain type and has one bool for parameter, but we could just grab every function, so this was pretty easy to develop on. And yeah, we had some special nodes we thought we would need for like the player skills, and that just made it easier for us. And one thing we ran into was that this is actually nice, really nice at editor time, but when running this, you still have no clue about where you are. And at that time, we added the visual debugging, which is the one thing that made all of this possible, really, because otherwise it would be a black box system. Yeah, and black box systems are never good. Okay, you push something inside and it's somewhere around this, but with the visual debugging, we could actually see where our logic is in this current frame. We could, as we can pause the editor, we can step to the next frame and see where our problems has. And this was really important to fix some bugs in the AI. And yeah. Still, there were some problems during development. And one is that the performance really didn't add up to the things we needed. Because we have this tree out of thousands of objects, and they're iterated in a stack, and stack operations aren't that fast in Unity. And we additionally had to save load the whole thing, so all the objects from the tree was saved and loaded again, because some states should be maintained after the save game is loaded. So we already heard about generating code. Yeah, and that's exactly what we did. We took the whole tree system and baked it into one single C# file. So for every character, we had one single C# file, or for every type of character, so not every enemy has a single C# file. And yeah, they get pretty long, like 50K lines of code. But at the same time, it was one function with only the objects we needed, and which was iterated with I enumerators, and this helped a ton. It was now 6 times faster, and the save load was rising, just really fast loading. And there are some things we want to add, because it's not perfect, and we just have, for the next project, we already see what we did in Shadow Tactics and what was not perfect, what we can add to improve our modularity, for example. So the subtrees are currently static, linked inside the parent tree, but probably we want to dynamically switch them in and out to optimize them, yeah, and improve the editor. I guess I told you that it's pretty shitty. So what everyone needs is something to maintain an overview of a growing logic. And we at Mimimi believe this is not possible with plain code. We did this, and it worked to some degree, but at some moment you just never know where you are. And okay, debugging in Visual Studio helps also a lot, but it's not enough. And at the same time, sometimes it's no need for pre-measure optimization. We wouldn't know if our node editor was giving us the performance we needed, but at the same time, we're doing the game first, and especially if we're doing the game first on consoles. And if you've written all this yourself, you can still optimize many things. And this kind of like this philosophy of Unity as a whole is get your game running.
Okay, so about the topic of getting your game running, I'll talk a bit about the console porting stuff, and most importantly, the optimization we had to do to get good performance on the consoles. So after release on 6th December last year, we had like acceptable performance between 40 and 70 FPS on medium PC hardware, and in the worst case it would drop to like 30 FPS. So that was kind of okay. And quick save and quick load times were also pretty fast. In our first tests with Xbox and PS4, the situation wasn't so great. So we had like only about 15 FPS, and quick loading didn't really deserve its name at that point, because it wasn't really quick. So we knew we had to do a lot to do that stuff. But let me show you what we had done in performance optimization up to this point already. So about AI and code trees, Phil already talked. So this already helped a ton. And then we also had to introduce time-sliced AI updates, which means that every 5 frames, all NPCs are updated, but every single frame, only like 20% of the AI is updated, and then they rotate out. So we just, cut the execution time into like a fifth, except for when an NPC is doing something special, like following a player or doing something other than walking on its waypoint system. The view cone also always was a big performance problem, but when getting really into the different settings we used for our cameras and shaders and render layer setups, we could remove many things that Unity would do by default, and we just had to select some correct settings, and then Unity wouldn't do the stuff by default anymore. So that was just, yeah, getting down to it. And we also tried to remove as much physics systems as we could, because physics always is kind of expensive, especially when you have large scenes like we had. The first part of this was combining and optimizing our collision matrix, and reworking some systems to no longer even use colliders, so just check stuff by code. So the target for consoles was 1080p with 30 FPS, with the same visual settings as the high settings on PC, and put the quick back into quick load because that was unacceptable. So the first thing we looked at was batching. The batching stuff Unity has, the static batching and dynamic batching, does a pretty okay job. We tried that first, but when you know the specific setups of your game, you might get more out of it if you're doing stuff on your own, because you can optimize stuff, especially like batch settings, especially to your game view, for example. So we use batches that are equal in size to the game view at all times. So the culling that runs in the background is just not doing that much more than it needs to do. And this was done for various objects. First is the visible geometry. That's what just is rendered in the game view. Then a different batch for shadow casters, which lets us reduce the draw calls for the shadow maps significantly. The visible geometry doesn't shadow cast anymore. The shadow caster is a specific mesh only for shadow casting. And then colliders, so every physics collider used for ray casting or for other, we don't really use physics like collisions or stuff like that, like rigid body collisions. We use it only for checks. And the grass we needed to render ourselves as well, because we threw out the terrain rendering because it was too expensive altogether. We built a big tool for that could just do everything. And very importantly, it didn't just delete the original meshes and create the batches in the scene. It would just disable the original meshes and save the information, which batch was created from which renderer, so we could just always switch back and forth and test the perfect settings and never lose the actual level geometry that the game designers built. And this reduced draw calls pretty drastically, like almost cut it in half usually for every scene. And this just freed up some CPU times that was used for rendering and gave the GPU some more breathing room. And as Phil already mentioned, we had a bit of a problem with the hierarchy. This is a screenshot of one of the enemies and its rig, so the animation bones that are imported when importing the model to Unity. And it's getting pretty deep. And we already heard when moving objects deep in the hierarchy, it's getting more and more expensive the deeper they are in. So at first we started by removing some structure elements, like Phil already talked about. But the most important part was reducing the amount and depth of the moving objects below the NPCs. So at first, NPCs all had their logic objects, like skills and various like noise emitters and stuff like that, had parented under their, childed under their moving navmesh agent. So all these logic objects would move with the NPCs, which were like 50 different objects with varying depth in the hierarchy, and this was just not needed. every of these logic objects had a reference to the character already, so it just could reference the position of the character and not the position of itself. So we just moved everything out in parallel to the character, and then we were down to like 10 or 15 moving objects under the character. Also, we used the optimized game objects import setting for the NPC models, which reduced the amount of rig objects, like bones and stuff, that were used, that you can see down below. This is all the rig. And this is what it looked like during runtime then. All the dark gray stuff, which is currently disabled, is the character stuff that is actually parented now under the moving character. And yeah, that's quite a big change. I think it went from 22 layers of depth to 11 layers of depth and just a third of moving objects. And yeah, this is what gave us the most drastic performance increase of all the things we did. So I can only say, yeah, keep your hierarchy flat. Okay, so we also did some thinking about the NPCs and what they, I don't know, would do or need to do when they are off screen. And we used the culling group API from Unity to check or get events when a character was entering or leaving the game view. So we could then, with this information, turn off specific logics that were running on the AI that we wouldn't need when they're off screen, like animation handling and velocity calculations and rotations, stuff like that. Everything you need to make the NPC look nice, you just don't need it. And the biggest thing that came out of this is that we switched to a more simple movement when characters are off screen. When they are on screen, we still use normal navmesh and navmesh agent movement. But as soon as they leave the screen, we just move them along their waypoint every few frames at the same speed the normal navmesh agent would have done it. And this, in one point, reduced obviously the navmesh agent pathfinding costs, but additionally, it reduced the amount of moving objects per frame. And as I already talked about, moving objects is very expensive, so this also helped reduce the amount of moving objects altogether. Additionally, we looked at our update calls and read about on the internet and whatever that Unity updates have some overhead sometimes. We're not really sure what is causing them, like the communication between your C++ code and C# code, or the checks if an object has to be updated or whatever, but we actually managed to combine the 4,000 update calls that were running on NPCs and their connected logics to one through an update handler, and checking if an object has to run, like if it is enabled, or do we need the system at the moment. It was done through simple booleans that states on the object that was saved and could be checked pretty easily without needing to check for null references or deleted objects or something like that. So this was all in all pretty fast and gave us a good amount of performance increase as well. So in the end, the results were pretty promising. So we actually reached our target of 1080p 30 FPS on consoles. Also with most of the PC high settings in place, we had to reduce a bit of shadow and post-processing quality on Xbox a bit more than on PS4, as usual. And on Xbox, there's even one small area where it might drop below 30 FPS, but yeah, nobody will find that. Save load also got a lot better, so we actually have a quick load now again on consoles, which is actually even faster than on the current PC version, which is pretty amazing. Okay, so in conclusion to all the optimization stuff, what we noticed is that Unity really doesn't know what exactly you are doing with the editor and with the API that it provides, which is fine for most projects or many projects, but we had to squeeze every milliseconds out of this thing. So we had to reinvent the wheel sometimes and do stuff on our own because we knew we could improve on it, because we knew the specific setup of our game and yeah, could optimize the stuff based on that. And yeah, that's always, I think, pretty helpful to just analyze your game, analyze what it needs, and then based on this, if you need performance increase, yeah, check that out and look into the systems you don't need sometimes or you could improve on. Okay. That's about it.
Thanks for watching. And we're also currently looking for talented devs. So if you speak German, we are happy to hear from you. Otherwise, we will be around. If you have any questions, just come up and talk with us.
Or now, I don't know if you have time left to do a Q&A? No. No? Okay. Then just hit us up anywhere around these stages.